Okay, if you were to lift a mass up in a gravitational field, you would do work on that mass and you would give it gravitational potential energy. So let's just kind of quickly diagram that right here. And I'm just going to use a ramp as our way of getting that gravitational energy back. Here's a bowling ball, right? If it's on the ground, we'll say that it has no gravitational energy. But if we were to do work on that bowling ball and lift it up to this ramp, we'll say this is the work done. Where would that energy go? Right? Conservation of energy says that we can't destroy it, it has to be somewhere. And so I think we'll all remember that it gets turned into peg. And we can do the calculations here. We know that work is equal to force times distance, and we know that that amount, that quantity, whatever the force times distance is going to be equal to mgh, the equation for gravitational potential energy. And when we release that bowling ball, it's going to come down here and it's going to have kinetic energy. And we also know the equation for that, right? How does all of this connect with what we're talking about over here? Well, it's these transformations of energy. When we do work on the bowling ball to lift it up to a higher energy state, that is just like doing work on an electron, lifting it up to a higher energy level. But here in the mechanical model, doing work is actually applying a force on the bowling ball and lifting it against a gravitational field. We could do the same thing here. We know that this electron is attracted to the positive plate, right? There's an electric field within these two charged plates. And if we apply a force against that, we lift that up, we could do work on it. But generally, in a hydrogen atom, which has one proton and one electron, you excite the electron up to a higher energy level by zapping it with some electricity or some high energy radiation. In any case, we input some energy, right? And over here, we input mechanical energy by actually applying a force. Here, we could apply a force against this electric field, but in an atomic state, normally it's just done with electricity. We could zap it, we could electrocute it, and that excites the electron and it jumps up to a higher state. Now, as the bowling ball comes back down to a lower state, it changes the energy from peg to kinetic energy, right? Well, as the electron drops down to from a higher energy level to a lower energy level, it's going to release a photon. Now, a photon is a new idea. It is a particle of light. It's a beam of light. As far as we're concerned, it's going to release some light. But in the model that we're using, it's just a little particle. And the reason why they say that is if you think on this ramp, I could lift this bowling ball up anywhere I wanted on this ramp, right? Here's a certain height, but I could take it to here, there. I could go anywhere and release the bowling ball from that height there, and then it would come down here, transfer, and we'd get a little bit of kinetic energy. But I could do, there's an infinite number of release points along this ramp. What's special about the emission of a photon via electron energy level transmission transition is that the electron can only go between certain energy levels. So I want you to look at this chart right here. Here is the lowest energy state, and you can see the energy that it has is 0. Now, EV stands for electron volts, and it's just a very, very small unit of energy. Here's the conversion right here. 1 electron volt is the same amount of energy as 1.6 times 10 to the negative 19th joules. So that's really a very, very small amount of energy, and that's why they came up with this new unit of energy. Well, if you were to lift this electron from the ground state up to the first energy level, you would be giving it 10.2 electron volts of energy. And as it dropped down, it would emit a photon with exactly 10.2 electron volts of energy. If you were to lift it up to the third energy level, n equals 3, and let's just say it only dropped back down to 2, it would be the difference between these energy levels that is now kind of missing or that needs to be accounted for. And the difference between 12.1 and 10.2 is 1.9 electron volts. And then you would have a little photon be emitted that is exactly 1.9 electron volts. And so all of these little arrows here You can see the absorption arrows are what happens when an electron absorbs arrows. It goes up to higher energy level. And then the emission arrow is when the electron drops down to a lower energy level and emits a photon. Ionization is a fancy word for you remove the electron completely from the atom. This n equals infinity is just an idea, but you give it so much, you give the electron so much energy that it actually leaves the atom and doesn't fall back, it escapes. So these different arrows are all the different transitions from the higher energy levels to the lower energy levels. You can see the different kinds of light. These are large energy transitions, and so they have high energy ultraviolet light. These are in the middle energy level transitions, and so that's visible light. That'll be energies that our eyes are sensitive to. And these are pretty low energy level transition, right? 12.8 to 12.1. That's only 0.7 electron volts of energy. So that's relatively low. And it's so low that our eyes aren't sensitive to it, and it's in the infrared range. So that's what's happening. We're taking a mechanical model where we do work on an object, a bowling ball. We store it as mechanical peg, and then we get that out as kinetic energy. Here, we will do work on an electron, or we will excite an electron to a higher energy level. And as it falls back down to a lower energy level where it kind of wants to be, it's the most comfortable at the lower ground state, it releases the extra energy that it absorbed in order to get up here. It absorbs energy, and then when it drops back down, it releases it as a photon of light. I'd like to just jump to this slide here just quickly to talk about the energies. Now, we already said the energies of the photons is equal to the difference between the energy transitions. Well, that's E right here. This E is the energy of these transitions, and that E here is the energy of these transitions. The only tricky part, or one of the tricky parts, is the energy transitions are in electron volts in this diagram. However, H, Planck's constant, which is used in both equations, is in joules right here. You can see joules right there. So any energy transitions that you get from this diagram, you need to convert from electron volts into joules, and then use that energy here. And then you can plug in Planck's constant and divide over and get the frequency. This is the exact same equation, but it's kind of solved around for lambda. I'll do a quick thing over here. Remember that the wave equation, c, the speed of light, is equal to frequency times wavelength. Well, if you were to solve that for frequency, you would get frequency is equal to the speed of light times the wavelength. We're going to take that and we're going to say, all right, instead of saying the energy of the photon is equal to h times frequency, I'm just going to use this right here for frequency, h, and then c over lambda. And so this equation right here, let me get this sheet of paper. This equation right here is the same equation as this, but it's just solved for lambda.